All right, let's try to write the epsilon n proof for the following statement. If the sequence AN converges to A and the sequence BN converges to B, which is non-zero, then the sequence AN over BN converges to A over B. All right, let's write down its definition. All right, for all epsilon greater than 0, there exists a natural number capital N such that as long as n is greater than capital N, then we can make sure that the absolute value of AN over BN minus A over B is less than epsilon. All right, so let's start with the conclusion and then try to fill in the rest. All right, by finding the common denominator, we can put together those two fractions. All right, then I'm going to subtract AB and add AB in the numerator. We have this, right? The equality still holds because we're not really changing anything. Then we can apply the triangle inequality to the numerator. We have this. And we can kind of distribute the absolute value sign to the denominator. All right, so I'm going to focus on controlling this denominator here, absolute value of Bn first. Right? Since the sequence Bn converges to B, so we know that there exists a natural number, capital N1. So as long as n is greater than capital N1, we can make sure that the absolute value of Bn is greater than absolute value of B over 2. Right? This might be a little bit strange because we usually have a less than, but we want the lower bound in this case, since we want to be able to replace the denominator with the smaller denominator so that we can have a larger fraction. Right? So by replacing this, we're going to get something like this. Right? So I replaced the absolute value of Bn by absolute value of B over 2. So we get absolute value of B squared over 2. Right? I kept this absolute value of B, so I put it here. Right? I added 1 to absolute value of A. So making the numerator bigger, that's fine, right? All right. Then next, we try to control absolute value of AN minus A. Because the sequence AN converges to A, we know that there exists the capital N2, such that as long as n is greater than capital N2, we know this. So here, I want to have epsilon over 2 here, but I need to cancel this guy, so I put that on the bottom. And I have this guy on the bottom, so I put that on top so that we can cancel that. So I'm going to put that in there, right? Then I'm going to control absolute value of B minus Bn. Since sequence Bn converges to B, we know that there exists a natural number, capital N3, such that as long as n is greater than capital N3, we can make sure that the absolute value of B minus Bn is less than this expression here. So we want to have epsilon over 2, but we have absolute value of A plus 1 there, so I put that on the bottom. So I have this guy on top, on the bottom, so I put that on top. Right? So I'm going to put that in there. Right? So since we want to use all three inequalities, so we have to set the capital N to be the largest of all three. So maximum N1, N2, and N3, which is a natural number, obviously, such that as long as n is greater than capital N, we have, right, so here, let's look at this common factor on top and bottom. Right, so if you look at this, right, so you can see that they're a common factor. So I'm going to cancel those out. Right, so here's another common factor on top and bottom, so I cancel those out. And then here's another common factors on top and bottom, so I cancel those out. Right, so what's left is epsilon over 2 plus epsilon over 2, so therefore it's equal to epsilon. Right, so therefore for all epsilon greater than 0, there exists a natural number capital N, such that as long as n is greater than capital N, we can make sure that the absolute value of an over bn minus a over b is less than epsilon, right? Hence, the sequence an over bn converges to a over b, right? That's it. I hope that this was clear.